Hello everyone, my name is Ruiqi Wang. I'm a PhD student from Smart Lab at Purdue University. Today, I'm very happy to introduce our paper entitled Feedback Efficient Active Preference Learning for Socially Aware Robot Navigation. Let's start with a background introduction. As robots are more integrated into our daily life, they will be sharing space with humans. Socially aware robot navigation in human-filled environments becomes an important problem, where a robot is required to optimize its trajectory to maintain comfortable and compliant spatial interactions with humans, in addition to reaching its goal without collisions. Next, I will introduce previous works. Generally, there are two main streams, model-based and learning-based. And within the category of learning-based approaches, there are two types, reinforcement learning and inverse reinforcement learning. While existing learning-based methods have achieved better performance than the previous model-based ones, they still have drawbacks. RL depends on handcrafted reward that is unlikely to effectively quantify broad social confidence and can lead to reward exploitation problems. Meanwhile, inverse reinforcement learning suffers from the need for expensive human demonstrations. To solve these limitations, we propose a novel human-in-the-loop reinforcement learning framework, namely feedback-efficient active preference learning, or FAPL, for socially aware robot navigation. FAPL is a purely data-driven method that tailors robot behaviors to human expectations and comfort, without massive reward or feature engineering required in previous research. Also, we introduce hybrid experience learning, including curious exploration and expert demonstration to improve the efficiency of human feedback and samples. Before introducing the details of our approach, I'd like to talk about the motivation of our work. Firstly, the reasons why we use active preference learning are that compared with RL method, it can distill the reward model from human preferences rather than having it handcrafted, covering social confidence more intuitively and comprehensively, and can avoid reward exploitation problems, leading to more natural behaviors. Also, compared with RL methods, it can introduce expert intelligence without suffering from expensive and noisy human demonstrations. Secondly, the reason why we need feedback efficiency is that to achieve good performance with active preference learning requires sufficiently frequent human feedback. Thus, it is essential to improve feedback efficiency so as to reduce the abundant human workload. Next, I will introduce a framework of our FAPL method. The FAPL is composed of two parts. First is hybrid experience learning, and second is agent learning. In hybrid experience learning part, there are two components, expert demonstration and curious exploration. Also, in agent learning part, there are two components. First is active reward learning, and second is all-policy learning. The robot agent begins with curious exploration, where it is encouraged to take different actions and reach diverse states through a state entropy-based reward. The collected exploration experiences are stored in an experience buffer along with the expert experiences from human demonstration. And the pre-trained policy from curious exploration is regarded as the initial policy in agent learning part. Next, human teachers express preferences for a pair of robot navigation trajectories from the buffer based on which the reward model is learned. Meanwhile, all samples are updated with a new reward value from each new generation of reward model during the active learning process. Finally, the robot agent utilizes the updated samples to optimize the policy to get maximal return from the reward model distilled from human preferences through all-policy reinforcement learning. Next, I will introduce our simulation experiments. We used an OpenAI gene-based simulation environment for training and testing. In experiments, we compared our proposed FAPL with other four SOTA methods. We also built up one evaluation model called APL, which removes hybrid experience learning from FAPL. The left figure shows that our model leads to higher success rate than all baselines, especially when facing a high volume of humans in the environment. Also, combining the indicators of navigation time and discomfort frequency shown in the right table, our FAPL leads to robot behaviors that respect human comfort distance more without sacrificing too much time due to lazy behaviors, such as waiting still for all people to pass. In addition to simulation experiments, we recruited 10 human participants to conduct the real-world experiments. Here are some sample videos from our real-world experiments. We can observe that our FAPL leads to more long-sighted and natural robot behaviors. After each real-world test, the participants were asked to fill a questionnaire to rate robot behaviors of different models in terms of comfort and naturalness, using Likert scale, with 1 being strongly disagree and 5 being strongly agree. Also, we asked all participants an interview question, after all, that could you share your preferences and explain reasons behind? From the questionnaire responses as shown in the left figure, our model performance is better than the best performing baseline and the aberration model in terms of human comfort and behavior naturalness. Also, from the interview responses as shown on the right, we can see the reasons why the robot behaviors of our model are preferred by humans, including long-sighted decision behavior and the behavioral naturalness. To sum up, in this paper, we present FAPL, a feedback-efficient active practice learning approach for socially aware robot navigation that distills human comfort and expectation into a reward model to get the robot to explore the latent space of social complaints. Our experiments show that FAPL can lead to more desirable and natural robot navigation behaviors than baseline methods. We also show that by introducing hybrid experiential learning, the efficiency of human feedback can be improved. Here are the references. Thank you for listening. If you have any questions, please let me know.